So now we're going to start looking at alkanes specifically. And this is going to be a lot of the pattern for any of the functional groups that we work with. Is that we start by doing some nomenclature, and then after that we get into some reactions of those functional groups. Now for something like alkanes, the reactions piece is very, very short. Because as we said earlier, alkanes really don't do a whole lot. So what we're going to be spending most of our time on in this first part is nomenclature. And that's because the nomenclature for alkanes is the basis for the nomenclature of every other functional group that we're going to learn. So all nomenclature within organic chemistry, and the nomenclature in organic chemistry is a lot more different, is very different, and a lot more complicated than what you did in general chemistry. And that's because, as you've seen already, organic molecules can get fairly complicated fairly quickly. But the real key here is making sure you learn your basic rules, which is what we're going to cover right now with alkanes. And getting a good grasp there, because everything that we do with alkanes is going to contribute to all of the nomenclature that we learn later on in this course. So for every functional group that we learn, the straight chain alkanes are what control everything. In other words, you have to know these straight chain alkanes. And at this point, you're going to need to know them up to 10 carbons. And if you don't learn the nomenclature for these first 10 alkanes, everything beyond this is going to be, almost impossible when it comes to nomenclature. So the first couple are usually the hardest because there's not really a good pattern with their nomenclature. Once we get up to 5 carbons, they become pretty easy. So 1 carbon is methane, 2 ethane, 3 propane, and 4 butane. Above this, if you know your normal numerical prefixes, the rest of these become pretty easy. If you think about what do we call a shape with 5 sides? Well, we would call that a pentagon. And so alkane with 5 carbons is pentane. What's a shape with 6 carbons? Or with a shape with 6 sides is a hexagon. So 6 carbons makes hexane. And so on. Heptane, octane, nonane, and decane. So that's where our nomenclature starts. And again, you just have to know these. Now, not everything is this simple, that it's just a straight chain either. So what happens when we have groups coming off of a chain? So like this. So I think we can see pretty clearly we have a straight chain of 5 carbons. And as we'll see in a little bit, we call that the parent chain. But what happens with this other group? So something that comes off the parent chain is known as substituent. And so we also have to name that. So how many carbons are in this substituent? The answer here is just 1. Now, it's a common mistake here to say 2. And if we say 2, it's because we've referred to that carbon. But that carbon is not part of the substituent because it's already part of the parent chain. So there's only 1 carbon in the group that's not part of the parent chain. So what do we call it? Well, if this was a parent chain by itself, a 1-carbon molecule, we would call it methane. But we need to distinguish that it's a substituent as opposed to a parent chain. And to do that, we get rid of the ANE and add YL. So a 1-carbon group is a substituent, becomes methyl. What if we had a 2-carbon substituent? So again, I'm just going to highlight our parent chain here in green. And you can see now we have a 2-carbon group coming off the parent chain. So 2 carbons, we know the name is ethane. But as a substituent, again, we get rid of the ANE and add YL for ethyl. And so this would mean that a 3-carbon chain is propyl and 4-carbon chain is butyl, and so on. All right, so now we want to actually start naming some compounds. So let's do the following molecule. So what we're doing is known as the IUPAC system of nomenclature. IUPAC stands for International Union of Pure and Applied Chemistry. And among many other things that this organization does is they set our standards for nomenclature. Now, to be perfectly honest, Organic Nomenclature Rules, they publish a book, and I think it's approximately 1,300 pages. So, we're certainly not going to learn all the rules of nomenclature, but there are certainly a lot of rules that exist for nomenclature. And that's, if you think about just how quickly an organic molecule could get complicated, it probably makes sense that there's the need for that many rules in order to be able to name compounds. All right, so how do we do this? Well, let's take this object and grab it onto a new page. All right, so there's our molecule again. So step 1, find the parent alkane. What do we mean by that? Well, this is the longest consecutive chain of carbons. And it could be in a straight line right across the molecule, or we might have to take sort of a zigzag path to get there. But the important thing is that it's the longest consecutive chain. Another way to think about it is that it's the longest chain in the molecule that you can draw without lifting up your pencil. So our longest chain in this molecule we can see is here. Now, what if we had two chains within the molecule that are tied? What do we do in that case? Well, in that case, we have a series of tiebreakers to go through. The first thing we would use to break the tie is that we would choose the chain with more substituents. And one of the reasons for that, in many cases, the more substituents you have, the simpler your substituents are, and the easier they become to name. Now, if that doesn't break our tie, then we look at the first substituent. And we see which one is nearest to the end. If those are the same, then we look at the second substituent on each chain and see which of those is nearest to the end. And we would go through until that broke the tie. If that still doesn't break the tie, then we look at the first substituent in each chain and choose the one that comes first alphabetically. If those are the same, we'd go on to the second substituent, to the third substituent, and all the way until we run out of substituents. If all of those are the same, then at that point we can be pretty certain that our two chains are equivalent. But we don't have to deal with any of those situations in this case. We have a chain here, and if we count it, we find that it's 8 carbons. So that tells us our parent name here is octane. All right, what do we do next? So we've got octane. Second step is to number the parent alkane. Once we number and the reason we need to number the parent alkane is once we name our substituents, we need to know where they are. And so that's what these numbers are going to tell us. Now, which direction do we number it? We can start here and go this way. Or we can go the other direction. So how do we determine which is correct? And does it matter? Well, the answer is yes, it does matter. So if we look at our blue numbers, where's the first substituent? So with the blue numbers, the first substituent is on the second carbon. The second substituent is on the fourth carbon. And the third substituent, because we have a total of 3 here, is on the fifth carbon. If we look at the pink numbers, our first substituent is on the fourth carbon. Second substituent is on the fifth carbon. And third substituent is on the seventh carbon. So what do we do at this point? So we look at the first substituent for each chain. With the blue numbers, the first substituent is on the second carbon, whereas with the pink numbers, the first substituent is on the fourth carbon. So given that the blue numbers have a substituent closer to the end, that's the direction that we go in. If those had been the same, we would have gone to the second number or to the third number as far as we needed to go till we got a point of difference. So let's put those numbers in again. All right, step 3. Name and number the substituents. So on the second carbon, we have a 1 carbon substituent, which we know is a methyl. On the fourth carbon, we have a 1 carbon substituent, which is a methyl. And on the fifth carbon, we have a 2 carbon substituent, which is an ethyl. Now, anytime we have 2 of the same substituent, whether or not they're on the same carbon, such as these 2 methyls, we can combine them. So at 2 and 4, we have methyls, but we also need to tell how many of them there are. So since there's 2 of them, these are going to be all of the same prefixes that you learned in general chemistry. So di for 2, tri for 3, tetra for 4, penta, and so on. So this becomes dimethyl. So finally, we can write out the name. In order to do that, we put the substituents in alphabetical order. Once we do that, but when we do that, so recall we have 2,4-dimethyl and 5-ethyl. When you alphabetize your substituents, any numerical prefixes such as di, tri, tetra, penta, so on, get ignored for alphabetization. So dimethyl gets alphabetized under M, which means that ethyl will come alphabetically before methyl. So 5-ethyl, 2,4-dimethyl octane. When you're writing out the name, you'll notice we put a hyphen in between numbers and names of substituents. If we have multiple numbers to list for a substituent because we have more than one, we put a comma in between. And then there's no space between the last substituent and the parent name.